All right, so one topic that we can deal with using concepts of probability and another idea called conditional probability, we're going to kind of break down what a test really does. Now, we're talking testing like if a COVID-19 test that looks to see if someone is infected with a virus, a drug test to see if they've been taking drugs. And I'm going to show you that their accuracy is not just dependent upon um, how accurately they catch drug users, because there's a lot more involved in a drug test than just saying that you tested positive, therefore you do drugs, and you tested negative, therefore you do not do drugs. That would only happen if the test was absolutely perfect, and no test out there is absolutely perfect. So there's four things that can happen. So I've set up, this chart, and this is generally the testing chart you want to use. So they either on this test are going to test positive or they're going to test negative. And two other things could possibly happen. They have the condition like COVID-19, or they do take drugs, or they do not have the condition where they don't have the virus or they don't do drugs. So this breaks it up into four possibilities. Outlined here by these four empty boxes. So we need to talk about these four empty boxes. So if you're in this location, a number in this location, you are a person that has tested positive when you actually have the condition. So this is known as a true positive. The test did exactly what it should have done. It caught the person that had the virus or did drugs. All right, we have down here tested negative, but they have the condition. So this would be a false negative. These people are the ones that we really need to be careful about, especially with the virus, that we tested them. We tested someone that actually has the virus. They got tested negative, therefore they go out into the world, and it's possible that they infect a lot more people. So having false negatives is very, very dangerous in a virus setting. Now, what's dangerous in the drug test setting? Well, that would be they do not have the condition. In other words, they do not take drugs, but they tested positive. So this group of people in the drug testing situation are being unfairly treated, because if you fail a drug test, you could A, not get a job, B, get fired from your job. Several consequences come from this. So having it as a possibility is very upsetting. So when we get to this is going to be a false positive. So these falses are bad depending on positive, I can't even spell, are bad considering what angle we're coming at. If we're talking about a virus, a false negative is very dangerous. If we're talking about a drug test, a false positive is very dangerous. But both of them are really bad because they're not doing what they're supposed to be doing. If you're testing positive, you should have the condition. If you're testing negative, you should not have the condition. So this number down here is another safe one. This one is a true negative. In other words, you don't have the virus or you don't do drugs, and the test actually said you don't have virus or you didn't do drugs. So the two areas which are good are the true positive and the true negative. The other two are what tests are trying to avoid, the false positive and the false negative, because they cause problems in many situations. Having already worked with tables and probability, you should be somewhat comfortable with reading them and pulling information from them. Now, there's a lot of probabilities we can create here, but there's some that are very specific to the information we need from this table. One of them is called Prevalence. What's going on here? And hopefully I spelled it right, but if I didn't, ignore it. Prevalence means what is the percent of the population that has this condition. So if we knew the percent of the population that we would suspect that had COVID-19, it would actually affect the numbers in this table of how the true positives and the true negatives and all that stuff fall. So the prevalence is the number of conditions, ones that have COVID-19, ones that actually do drugs, divided by the population. Now, in this case, the population is the number of people that were in this experiment to see how well this test catches the virus COVID-19. So the people that have conditions, there's a total of 125 of them, and then it's out of 500. So when we come up with this prevalence probability, it's going to be 125 divided by 500, which is the same thing as, what is that, 1/4? Which is the same thing as 25%. So 25% of the population in this experiment has the virus. So that means 75% of the population does not have the virus. But prevalence is how many have the condition. What is the percent of the population that has the condition? All right, the next probability is the one if you go to a drugstore and you buy a drug test. You're going to drug test your kids, I don't know. So when you do a drug test, the probabilities or the percentages they give are based only on that column. The probability we generate from this column is called sensitivity. So basically, how sensitive is the test to actually catching those that have COVID-19? So to find the sensitivity, it's literally just the true positives divided by those that have the condition. The total number of conditions. So in this case, this example, the true positives is 112. And then those that have the condition are 125. So the sensitivity of this test is 112 divided by 125. There we go. 112 divided by 125, and change it to a percent. We'll multiply by 100. So 89.6. So this would be 89.6% sensitivity. So all that means is it is the probability that if you have the condition, so there's the conditional probability, you have to have the condition first. It's only going to catch 89.6% of these people. So if you want to think about it, 10% of these people that have the virus are not going to get caught, and they're going to think they don't have the virus and go out and spread more of it. Okay, so that's one of the probabilities that we can get out of this table that are informative. One that is similar to it, I'll do it in purple, is this column. And if we look at this column, it's called specificity. Specificity. Again, if I misspell these words, forgive me. Now, specificity is true negatives divided by no condition. All those that do not have the virus. So the true negatives in this case are 300. And we're going to divide that by all the people that do not have COVID-19, which would be the total here of 375. So 300 divided by 375, 300 divided by 375 gives us this decimal, and if we multiply that by 100, we would say the specificity has a 80% chance. So if you do not have the virus, this test will be accurate 80% of the time. So that means 20% of the time you're going to be a false positive. Now, if you have a false positive in this case, it's not disastrous. You don't have the virus, but they'll probably quarantine you. So it's a little of an inconvenience, if anything. Another probability, conditional probability, that we can pull off of this table is called the positive predictive value. Basically, it only concentrates on testing positive. So we're looking at this row, and what it's going to be asking for is, if you tested positive, what is the probability that you actually have COVID-19 in this case? So we're going to be looking at true positives over all positives. So this is known as PPV, abbreviation-wise, and it is true positives divided by all positives. So this is just a probability that says if you test positive on this test, what is the probability that you actually have the disease? Now this one should be really, really high, because we want to make sure we're really catching only those that have the disease. So in this case, the true positives being 112, and the all positives being 187, we're going to get a probability, let's see here, 112, 187, and then times this by 100. So about 59.9, almost 60%. And this being so low, I guarantee you this test would never make it to market, because this probability should be above 90% for it to even be really used. Now, I read an article last year about the drug tests that they use at traffic stops, and they don't release the data so that people can see the sensitivity and the specificity and the PPV at all. They don't advertise it, but people go to jail based on these drug tests. I think the article, I posted it in Moodle, so if you want to look at it, it's really quite interesting and kind of scary. All right, so let's go with bright colors. The next and last conditional probability is going to deal with this one. It's not as strong as PPV. This is the tested negative. And here, the only one we're worried about, of course, is if you tested negative, you want to make sure you're a true negative. So this is called the negative predictive value, also known as NPV. So this is true negatives divided by all negatives. So in this case, it's going to be the true negatives is 300 divided by all the negatives, which is 313. So 300 divided by 313. And multiply that by 100. And we see this test is really good. If you test negative, it is catching your negative people quite well, which isn't great in this case. It's great for a drug test, but if you're a COVID-19, we're not too worried about, people that don't have the virus. We're much more worried about the people that have the virus. Oops, I forgot to read the number. 95.8. So this would be 95.8% accuracy. So based off all these percentages, especially this one and this one here, the 59.9, I would say they need to go back to the drawing board and create a better test. So prevalence is one of the concepts that make a test. Prevalence is one of the things that will make a test either better or worse. So the prevalence of tuberculosis in the Philippines is rather high compared to like the United States. They have a prevalence anywhere between 1 and 2% of the population is infected with the tuberculosis virus. So their prevalence being, let's say, just 1%, I want to use a test that is 90%, 98% accurate, which is also known as sensitivity, and also has a specificity of 95%. So these are really high percents. And I want to see what effect the prevalence has on the PPV and the NPV of this test. Now, before we can do anything, we need to have a population we're going to experiment with. So we're going to use this on 750 people, and what would we expect the table to look like based on all of these percentages? So we're going to start off with the prevalence. It's the best one to start off with. So we have 1% of my 750 people, if we're in the Philippines, that we would expect to have tuberculosis. So to do 1%, remember you have to take 1 and divide it by 100. And to take a percent of a number, you're going to multiply. So this is going to equal 7.5. Now, you can't have 7.5 people, and this would be with TB. We're trying to base this table on whole numbers, so we have a choice. We either round it up or we round it down. I'm of the opinion of rounding down, and my lab makes you do the same thing. So the total number of people that have TB is going to be 7 because we're rounding down. So if we have 750 total people, then 750 minus 7 is 743. Do not have tuberculosis. So the prevalence gives me 2 numbers that I can put into my table right off the bat. All right, so now it's up to the sensitivity, which is how accurate the test is. So 98% of the ones that have the condition of 7 is going to be the true positives. So this is true positives. So I have to take 98% of 7. So let's see here. 98% of 7. And remember, we're going to round down, so this is going to be 6. And this is the main reason to round down, because if you go to 7, then that leaves 0 someplace, and that's kind of boring. So we're going to say 6 tests positive, and 1 is going to test negative. All right, so that would be the 98 over 100 times 7, which gave us 6 when we round it down. All right, and then there is, let me change colors for the true negatives that we're going to be looking for, which is related to specificity. So the specificity of the test was 95%. So it's going to be 95% of those that do not have tuberculosis, which is 743. So calculation-wise, this is going to be 95 over 100 times 743. So that leaves us with, remember, we're rounding down, 705. So that would be 705 are going to be my true negatives, and that leaves 38 people. So 38 will go here, and then basically my table's done. I can fill in the rest by just adding. This is 706. This is 44. And we could double check. 7 plus 743 is 500. And 706 plus 44, is 500, 750. And 44 plus 706 is also 750. All right, so now I can do PPV and NPV based on the numbers in this table. All right, to do that, I'm going to erase a little bit to give myself some space. All right, so PPV for this table is the true positives divided by tested positive. So the true positives here are 6, and the tested positives here are 44. So this is equal to 6 divided by 44 times 100, 13.6%. So the positive predictive value is extremely low. All right, so let's look at NPV. How many times will the test show that you do not have tuberculosis accurately? So this is the true negatives divided by tested negative, which in this case will be, and I'll change colors, the true negatives over the tested negatives. So that's going to be 705 divided by 706. That's really close to like 99%. 705 divided by 706 times 100. And I really should go inside because of a thunderstorm. So that's 99.9%. So we get 99.9% NPV. So this test is really, really good at catching those people that do not have tuberculosis. The problem is it doesn't do so hot catching when you test positive of catching the ones that really do have the disease. Out of all the 44 that tested positive, only 6 of them really had the disease. And that's all because of this 1% up here. If we went back and changed that 1% into 10%, it would increase our PPV dramatically. The next major topic that we're going to be dealing with is statistics. Now, statistics is the gathering, organizing, analyzing, and drawing conclusions based on data that we have found, collected, experimented with. All right, so gathering, we're not going to get much into the gathering. It actually turns out to be an entire course in statistics on how to gather this information correctly without having it being skewed one way or the other. That being said, a lot of pollsters will ask, they'll call up somebody on the phone and they'll ask them questions that make them lean towards answering the question the way you want them to. So sometimes it could be what's considered deceptive gathering of data, and those are the ones you have to be a little bit cautious about. If they sound a little bit like they're leading you on in the questioning, then it's not a very good collection of data. The organizing of data is something else that we're not going to get into. It would be doing the bar graphs and these things called histograms that look like bar graphs that are shoved together, pie charts, line graphs, and you might see some of these as we go through some of this data, but most of it we're going to be dealing with the raw numbers, and we're going to do the analyzing and a little bit of drawing conclusions. So pretty much the most important parts of statistics are the gathering of it, making sure you're collecting the data correctly, accurately, and unbiasedly. And then finally, drawing the conclusions from the data is really important too. And so those two we're going to just touch on very little bit, and the rest of it we're going to just do what we can with it. So analyzing mostly analyzing. So here's some data that I just looked up on the internet. I was looking up high temperatures in Raleigh, North Carolina. I found some for Greenville, and I didn't put all the data out here for the month of April, so I just picked every fifth day. So the high temperatures in April of 2020 went 60, 80, 65, 65, 73, 71, 65 in order as I went through the month. So one of the first things we're going to do is we're going to organize this data so that it is a little bit more to our liking, because there's a few things that I cannot do the way it's written now, but if I get it ordered correctly, then I can answer a few other questions. So let's put it in numerical order. Smallest number first, which would probably be that 60. Let's change colors. So we'll have 60. And then even if a number repeats, I'm going to write it down. So even though the element 65 happens 3 times, I'm going to write it down 3 times. 65, 65, 65. Now, when you're doing this, it's best to go through your original data set and cross out the ones that you wrote down. Because the most common mistake is when you're doing this, you forget to write one. So if you write it and then cross it out, then you'll know what's left over and you're less likely to make mistakes. Next biggest number, 71, and then 73. And then finally, 80 is the biggest number. So one thing we can say by putting them in order is the lowest temperature based on my data in April was 60. The highest temperature in April was 80. So that's one good thing that comes out of spreading it out like this. Now another thing is what's considered the middle number. When you put them in order, it's a lot easier to find the middle number. So to find a middle number with a very small string of numbers, if you do this with technology, it's done totally different than what I'm going to do here. So what you do is basically you count in. So there's 1 on the left, 1 on the right, 2 on the left, on the right, 3 on the left and the right, and the only number that's left in the middle is the 65. So the 65 is called the median. Basically the middle of the data. It's kind of like a median of a highway. It's in between 2 lanes of a highway. Another thing that we can get out of this data directly by putting it in order is we can find the repeat numbers. So these numbers here repeat 3 times, and all the other numbers are just once. The one that repeats the most becomes known as the mode. So the mode of this data is also 65. Now they're talking about 2 different things here. The median is just one number that happens to be in the middle of the data, and the mode is the one that happens to happen the most often. There are 3 65s. All right, one more thing that's not necessary to have the numbers in order is what's called the mean. Now we're used to a different word for mean. Mean is the same thing as average, usually. Now, average is a strange word. It could mean literally 2 of the words that are on my page right now. Average usually means the mean, but it also can mean the median. And by the way, it could also be the mode. So average is kind of a loosely defined word in statistics. So it's better if we're talking about an average, we usually associate it with a mean. Let me give you an example. Average salaries in the U.S. is $38,500. So when you read a sentence like this, little bells and whistles should go off in your head that the average salary in the U.S. is $38,500. usually when this statement is written, they are talking about the median. Some authors will actually say the median salary in the U.S. is $38,500. And the reason that average salaries are not usually used in data is that the data is what's considered skewed. And you can kind of get a hint on this. There are very few rich people. Remember, those top 1% of the richest people have more wealth than the bottom 10% or something like that. I forget what the stats is on that. But if we did the average as a mean, the mean salary is something like 143,000. And it doesn't make sense that you consider a mean salary because it really doesn't represent the average person. So when we talk about salaries, it's usually the median and not the mean. So what is the mean? The mean literally is just add them all up. So when you add a bunch of numbers together and then divide by how many, you get this number called the mean. And the mean, median, and the mode are what are called measures of central tendency. They all try to give a single tendency, single value to where the average is. So the mean, median, mode are trying to find that one number that represents an entire group. And it doesn't always work that well. Salaries, for instance, because even knowing that the median salary, the middle salary, if you listed everybody's salary up and you counted in from the outsides like this one up here, you would find that you would land on 38,500, which is kind of scary because that means 50% of the people make less than that and 50% of the people make more. But then you turn around and you add up all of these salaries across the United States and divide by how many people have these salaries, and the salaries mean is closer to $100,000. It kind of gives you an idea that the money is all leaning towards that top 50%. So it's kind of scary. Let me do an example of doing the mean. I haven't gotten to it yet. All right, so let's talk about finding the mean. Now, saying add them all up and divide by how many gets kind of tiresome, especially if you're writing it. So this symbol literally means add them all up, and we're going to represent data with the letter X. So X is data. Now the word data is interesting. It is singular and plural, kind of like moose. Moose being singular and plural for a moose, or the moose. So data in this case is going to represent all the x's and each individual x. So we have to be kind of careful when we use the word data or this variable x. So this is add up all your data divided by how many, and how many is going to be n. So n is how many. Okay. So I just need to add up all these numbers. So I wrote them all out because I couldn't keep them all in my head. So 60, and notice I did 3 times 65 instead of doing 65 plus 65 plus 65, which is fine, but this makes it a little shorter. Plus a 71, plus a 73, plus the 80, for a grand total of 479. So over here I'm going to write 479. And how many are there? There are 1, 2, 3, 4, 5, 6, 7 of them. So I'm going to divide by 7. So if I divide this whole thing by 7, I get 68.4. I'm always going to go a decimal at least. So this is approximately 68.4. So we have found that the median was 65, the mode was 65, and the mean is 68.4. So they're all rather close together, which we would expect for data that has a special feature called normal. Um, we'll talk about that more later. Another symbol for, the sum of the x's divided by n, we can also represent this with x bar. So if you see x bar in a formula, all it means is the mean. There is no fancy notation for mode, and there is no fancy notation for median, but mean is so important that it gets its own little notation. So the median has a little bit of a trick involved in it. The example that we did before, this one up here, had an odd number of data values, so when we moved into the middle, we were left with a single value, which is nice. But not all data is an odd list of numbers. For instance, I added on a few numbers here, and I made it 10. So off to the side, you can say n is equal to 10 right off the bat, because there are 10 numbers in this list. All right, so when I start moving in from the outside, one at a time, usually works better with like 2 fingers, I end up with 2 numbers in the middle. So I have a 71 and a 73 in the middle of this data, and I have to find the middle, which is in between them. So the easiest way to find a number in between 2 other numbers is to find their mean, or midpoint. So we're going to add them together and divide by 2. So the median here is going to be 144? Yeah, 144. Divided by 2, which would be 72. So the median for this data, even though it's not one of the numbers in the list, is 72. Now, if we go a little bit further, we can find something that is called quartiles. In other words, we're going to break the list into 4 equal pieces, 25% each, and therefore quartiles, quarter, 4 quarters, and $1. So to do quartiles on an even list, the middle is between 71 and 73. So what happens is you don't have to write it again, but I'm going to. The middle is in between 71 and 73, so the 71 kind of stays around, and then the 73 starts the second list. And I do this usually mentally, not on paper. And then technically, you find the medians of these 2 pieces. And they become known as your quartiles. Now, the one on the left is going to be called quartile 1, and the one on the right will be called quartile 3. Now, that seems a little odd that the left is quartile 1, the right is quartile 3, and that's because the median itself, this location, is quartile 2. So we usually just label that Q2, which makes sense because if you're the second quartile, that's 50% of the information. So the median is also known as quartile 2. All right, so now let's get back to finding the median of these 2 pieces, which turns into the quartiles. So both of them have only 5 numbers, so if we count in, 65 is the middle here and 77 is the middle there. If there were 2 numbers in the middle, if it was an even number list of numbers, then we would do the same thing that we just did, add the 2 numbers together and divide by 2. So what this gives us is what's known as the 5-number summary. So a quick review of what we found. We found that the median was in this location. And notice there's no number there, but when we added 71 and 73, we came up with 72. So this becomes our median, also known as quartile 2. Now, when we separated the list into 2 equal pieces, we found that the median of the left-hand piece and the median of the right-hand piece were respectively 65 and 77. So this 65 becomes known as quartile 1, The 77 becomes known as quartile 3. And then we have our minimum number to the left and our maximum number to the right. So this is what's known as the 5-number summary. So the minimum, the quartile 1, the median, quartile 3, and the maximum. So another thing that we could create out of this is what's known as a box and whiskers plot. So here I've tried to draw a number scale, kind of to scale, 5 units between each one of these numbers. And the minimum number being 60 becomes drawn like this. And the next, I'm going to make it a little taller. The next number up is quartile 1, which is at 65. So we get a nice long line here. And then the median is 72, so it's someplace around here. And then quartile 3 is 77, right about here. And then the maximum is 83. So we're going to draw lines for the ends and then a box in the middle. So the box in the middle represents the middle 50% of this information. So this one seems like it's spaced out really well, almost what's considered normal. All right, so let's find the 5-number summary for this data that I have here. And we'll notice some other things about it while we're going about this. First off, I highly implore that you count how many elements are in this list. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then just right off to the side, n equals 12. So we have an even list of numbers here. So therefore, when we do our median, we're going to end up with 2 numbers that we're going to have to add together. All right, so let's move from the outside in. There's a way of doing this with a formula, but I've never seen a student that actually enjoys doing it with a formula. They'd rather just count in. So 1 on the left, 1 on the right, 1 on the right, 1 on the left, and so forth and so on. Until we get to these 2 middle numbers. So the median has to be between these 2 numbers. And therefore, we do 11 plus 14 divided by 2, which turns into 25 divided by 2, which is 12.5. All right, so the median, quartile 2 also, is going to be 12.5. And again, it's not a number in the list, it's just a number to represent the middle of this data. All right, so when we get a split like this, we're just going to draw a line between the 2 lists and split them. Again, if we landed on a number, I would literally just cross it off and split the list that way. So if you land on a number, you would get rid of it. If you land between 2 numbers, you just split the list in half. All right, so we're going to split it here. When we're on the left, there are 1, 2, 3, 4, 5, 6 elements. So again, when we move to the middle, there's going to be 2 elements. And we're going to have to add them together and divide by 2. So 4 plus 5 is 9. If we divide by 2, this becomes 4.5. So this is Q1. All right, same thing on the other side. There are 6 elements, starting with 14. And if we move into the middle, 20 and 21 are the middle numbers of the right-hand list. So the median there is going to be 20.5. And 20.5 is going to be known as Q3. And then, of course, the minimum number is 3. The maximum number is 25. So let's put this information into a graph. This one I scaled because the numbers were kind of large. And the smallest number is going to go here. Let me change colors. At 3, so I'll draw a long dash at 3. The quartile 1 is at 4.5, so I'll put a dash there. The median is 12.5, which is here. And then quartile 3 is 20.5, which is way over here. And then finally the maximum is 25. So you get a feel that there's very little data at the end of this. 25% of the data is below 4.5. then a majority of the data is here in the middle. That would be 50% of the data. And then 25% of the data is down there. So this would be the box and whiskers graph of this 5-number summary. Now, the other thing you can find is the mean of this data. And then we can start discussing something that is called skewed data. All right, so really quickly, I have a shorter list of numbers here. I want to do a 5-number summary and talk about this concept of skewedness and find the mean of this data so we can kind of start leaning towards not always having to graph the information, but knowing 2 values, we should be able to tell if it's skewed data or not. All right, so here I have 9 numbers, a lot of repeats. Notice a lot of them are really small and very few are really large. Also notice that the minimum and maximum numbers of this list and the previous ones are exactly the same. So that idea that the distance between the largest and the smallest one is called range, it's not a super important number because you can see that these 2 lists, even though they have the same range, they're definitely not the same type of data or same groupings that we're going to get out of this. All right, so let's go for the median first. If there's 9 numbers, then the middle number is going to be that 4 because there's 4 numbers on the left of 4 and 4 numbers on the right of 4. So this is the median. But because it landed exactly on that number, we're not going to use that number when we split the list. So when we split the list, we'll have 3, 3, 4, 4. That 4 that's the median does not get counted. We'll have 5, 7, 15, and 25. And then we need to find the median of both of those lists. And the middle is going to be 2 numbers on this one and 2 middle numbers on this one. So if we add the 3 and the 4 together, I'm just going to write it off to the side here. We have a min, we have a Q1, we have a median, we have a Q3, and we have a max. All right, so the min we know is 3. We know the max is 25. Q1 is going to be 3 plus 4 cut in half. That's going to be 3.5. The median is 4. And Q3 is going to be 7 plus 15, which is 22, cut in half. That's 11. So we can graph this on the exact same number line I had for the previous example. So let's see here. The minimum is 3, so I'll have a dash here. The quartile 1 is 3.5. That puts a dash right there. The median is 4. That puts a dash right there. And quartile 3 is at 11, which is over here. And then 25 is way down here. So the whiskers part of it is from here to here and here to here. So the rest of it is the box. And you'll notice this box is different than the one above it, specifically because most of the information, you can talk about 75% of the information is less than 11. I'm sorry. Yeah, less than 11. And 25% of the information is between 11 and 25, which doesn't kind of make sense with this small list, but we'll go with it. So this data, since it's all scrunched up on the left-hand side, you would think it would be called skewed left. But that's not how it works. It's the tail end that gets the name. So this is skewed right data. This is the exact same way salaries in the United States are skewed. Most people make a little bit of money, and very few people make a lot of money. So that would also be considered a skewed right data set. All right, let's do one more thing while we're here. Remember, the median is 4. What I want to do is I want to find the mean and see how that compares in this data set. All right, so 3, I could probably do this in my head now. Erase. So I added up all the numbers, 3 plus 3 plus 4 plus 4 plus 4 plus 5 plus 7 plus 15 plus 25, and I got 70. And there are 9 numbers altogether, so the mean of this data is going to be whatever 70 divided by 9 is. So 70 divided by 9 is 7.8. So this is approximately 7.8. Now, to tell if data is skewed, you're going to use the mean and the median number and kind of compare them. 7.8 is right about here, so this would be x bar. And this line back here, let's make it bright pink, this is the median. So we can kind of say when the median is less than the average, the data is going to skew to the right. So the reverse of it is going to be if the median is larger than the mean, then the data is skewed left. Then if the median and the mean become about the same, we're going to call that type of data normal. So let's put it all together now. So this first picture is skewed right. And that is because the median ends up being someplace like here. Let's say the median ends up there. So here's your median. And the mean gets pulled to the right. So here's x bar. So if that's the case, you're going to get data that is skewed right. The tail is where the right-hand side is, not the peak side. All right, if data is skewed left, then what's going to happen is your median is going to be over here now, median, and your average, your mean, is going to be on the other side. So if the median is less than the mean, you are skewed right. If the median is greater than the mean, you are skewed left, and left being that tail right there. Now, if the mean and the median turn out to be basically the same, they land in the same area, then what we get is what's called normal. It's normally distributed data. It would be really great if salaries were like this. Most people would make about the same amount of money. Very few people would be poor. Very few people would be rich. A nice utopian society. It'll never happen. All right, so kind of like the previous example, I was showing you how data can be distributed differently, being skewed one way or the other, or normal. Another type of measurement which gets used much more often is this idea of closeness of data. Is it data that is packed really tight together, or is it spread out all over the place? So I have this simple example that I've used for years to kind of describe why we need this other measurement. So Mr. Smith has 2 sections that took the exact same test. Section 1 had those grades, and Section 2 had these grades. It's 5 students in each group, and if you did add up all the numbers and divide by how many, you would find the average of Section 1 to be a 70, and you would find the average of Section 2 to also be a 70. But if you look at the grades, they're not exactly the same. So for instance, if you scored an 80, and I didn't tell you what class you were in, and you kind of knew someone either scored higher than you or lower than you, this 80 is different than this 80. In the first class, he is number 2 in the class. In Section 2, she's number 1. So this 80 does not represent the same type of 80, even though the averages of both classes are exactly the same. You'll also notice if you start at 70, that in the first section, it's jumps of 10 that are going in both directions, where in the second section, it's just jumps of 5. So this next measurement is going to be basically an average, but it's going to be the average of the distance away from the mean. So when we start talking about distance, there's a neat little formula in algebra It's called the distance formula. And it's kind of, looks like this. And I like showing it just for the fun of it. You don't have to know this. But basically, this is where this next measurement is going to come. It's going to be the sum of a bunch of things that are subtracted first and then squared. So this measurement of closeness is called standard deviation. So how standard deviation works is it kind of acts like the distance formula, but then you also have to throw in it's literally the average distance from the mean, also known as x bar. So to find the average distance from the mean, we're going to, I'll shorthand this. There's going to be two different standard deviations that we're going to talk about. And generally, we'll lean towards the top one. The bottom one sometimes comes into play, but for most of my problems, we're going to stick with the top one. And its formula is pretty much the square root of, so we get that distance square root in there. Then we're going to have a sum of things. So this is going to take care of, all the additions between these subtractions that we're going to square, of a data value in the list. Like if you're in section 2, a data value would be 60, 65, 70, 75, or 80, minus the average, the mean, in both of cases, 70 in this case, squared. So you would sit here and literally take each number in the list, subtract it from 70, find that answer, square it, and add them all together. And then we'll do some other things to it. So this one is going to have an n minus 1 in the bottom. This is known as a sample, standard deviation. A sample being you polled a certain part of the population and you're collecting data on a smaller group than the whole. Now this other one, which has a Greek letter for sigma, which is basically the S in the Greek alphabet, it's very similar in formula. It is the sum of all these things subtracted and then squared. But instead of dividing by n minus 1, you're going to divide by n. So by dividing by a larger number, you're making the standard deviation actually smaller. So this one is more accurate if you could actually poll everyone. But most times you won't be able to do that, and that's why you're kind of stuck with the sample standard deviation. So this is population. Now, if we were going to sit here and calculate this out, I'll just do section 1. And we know that the mean of this thing is 70. So the way I've always been shown how to do this is you set up a table. You put in your data values. So you put your 50, 60, 70, 80, 90 here. And then you would subtract your mean from each one of them. So 50 minus 70 is negative 20, 60 minus 70 is negative 10, 70 minus 70 is 0, 80 minus 70 is 10, 90 minus 70 is 20. Then you would take each one of these numbers and you would square it. So negative 20 squared is 400, 10 squared is 100, 0 squared is 0, 10 squared is 100, 20 squared is 400. And then you would take all of these numbers and add them up. It turns out to be 1,000. Whew, tedious. And then you turn around and you take 1,000, and if we're doing S, we're going to take that and square root it, and before we square root it, we're going to divide by how many there are, minus 1. So this turns into the square root of 1,000 divided by 4. I'm not even going to simplify that. It does simplify, but I'm just going to calculate it out. So square root of 1,000 divided by 4. 1,000. So 15.8. So the standard deviation after all of that fun stuff of a sample is 15.8. I do not expect you to go through this process to find the standard deviation. So I'm going to show you how to do it on a spreadsheet much quicker, and it'll always give you the right answer, more than likely more so than doing this process yourself. Standard deviation by hand, I think it's much more reasonable to do it using a spreadsheet or a fancy calculator instead, because doing the calculation itself offers no insight into what is going on. So we'll start off with my section 1 and section 2 scores here. And you can find the mean of both of these data on a spreadsheet also. The only problem is mean is not a function of spreadsheets. I wish it was. They use the word average. So you're going to find the average of things. The first thing you have to type, of course, is equals, and then you type in average, and then parentheses. And then all you have to do is go up, click and hold on the first cell, and then drag down. So what'll happen is, even if I don't end the parentheses here and just hit enter, it'll take all of those numbers, add them together, and divide by how many there were. So it already knows what the numbers are and how many they are, so the computer does all the work for you. So the mean of this data is 70, kind of like what I told you. And I can use the fancy feature to copy the formula over. It'll add all the numbers above it and divide by how many there are. And again, the average is 70. All right, now there are two different standard deviations. Technically, even by hand, there are two different versions of standard deviation. One of them, this P1 that we're going to talk about first, is the entire population. So if you could survey 350 million people and ask them a certain question and get some information from them all and collect all this data and add them all together and divide by 350 million, then this would be the standard deviation we're talking about. Now, having a population standard deviation is really rare because it's very difficult to ask an entire population. Now, if we're talking about like a high school population, then we can start leaning towards asking all the students in a school a certain question, gathering all of their information and tabulating it and finding its standard deviation. Then we could lean towards a population standard deviation. But the more popular one is the sample. So if we're looking at a sample standard deviation, it's a little bit different. I was talking about it in the previous part of this video where I did 5 minus 1. So a sample basically just takes what you're dividing by and makes it smaller. Therefore, the standard deviation is going to be a little bit bigger. So let me show you how this works. Stdev is standard deviation for a spreadsheet. And you'll see some of these other ones up here. Oh, they put in dots. They're starting to get like Microsoft Excel. So Stdev parentheses, and be careful you don't include the 70 here. That's the mean. We're talking about the standard deviation of the original 5 numbers. Let me get that out of the way. So we can just hit enter there, and that one is 15.8. Now if I do this one, this is Stdev either .p or p. Both of them are exactly the same thing. .p is a Microsoft Excel version of the formula. Just the P is Google Sheets. I'm just going to use the Google Sheet one. I'm going to select the 5 numbers and hit enter. And you'll notice that the population one is smaller and this sample one is a little bit bigger. And the reason the sample one's bigger is we know there's going to be a little bit of error, so it makes the standard deviation a little bit larger to account for that error. All right, let's copy these two formulas to the right. It'll do exactly the same thing with section number 2 data. And you'll notice that, again, that the sample standard deviation is bigger than the population standard deviation. So that's how you find the standard deviation of numbers using a spreadsheet, so you don't have to go through and take a data point, subtract from its mean, square that number, and add it to a bunch of other ones, square root the whole. It just gets too tedious. Where this is much clearer, get you an answer that you're going to use. And pretty much a standard deviation, we're just going to use the idea in other calculations. Also notice that section 2's standard deviation is much smaller than section 1's, which indicates that section 2's data values are closer packed than section 1's.